Good. Welcome to reInvent. I know this is your first session for Monday morning. Let's start with a quick poll. How many of you use today a mobile app to start your vehicle remotely? I see a few hands raised. Thank you. So the topic for today's session is connected vehicle. So connected vehicle is the key enabler for the remote operations that you can do from your mobile app, especially do remote start, warm up your vehicle during winter time, and so on. So in an era of connected vehicles, it is crucial for customers to use real-time data insights to enhance customer experience and improve the operational efficiency. My name is Vijay Tope, Senior Solution Architect with AWS, supporting automotive customers. Along with me, I have two speakers. Yanni, she is a Senior Analytics SA, supporting automotive as well. And our guest speaker, he's from Uma Maheshwara. He's from Ford Model E Arc. He's a senior engineer, worked with us to champion this use case. We're going to discuss how Ford unlocked real-time insights using Apache Iceberg in AWS. This session explicitly explores Event Store, a key service for Ford's connected mobility, connected vehicle platform. So we have a packed agenda today. I'm going to start with an overview on connected vehicles, followed by how we can modernize using Apache Iceberg on AWS. We'll deep dive in Ford's connected vehicle platform, how Ford built and scaled Event Store, serviced by overcoming challenges and optimizing, leveraging Apache Iceberg. Okay, let's start with a quick overview on connected vehicles on AWS. AWS infrastructure allows you to easily connect and secure vehicles by building innovative mobility features and applications that can run both in the cloud and edge at global scale. On the top left is your secure and scalable automotive cloud infrastructure. As vehicles become increasingly connected to the internet and to various digital ecosystems, the opportunity arises to create a tailored and immersive user experience for the driver as well as passengers by the automakers. In the center, you see the vehicle, it can be a car, a truck, a bus, or a boat. Connected vehicle with built-in modem helps you to connect to the cloud and to offer a rich set of features by leveraging IoT edge computing building blocks, such as IoT SDK, serverless functions, serverless databases, security, and of course, machine learning at the edge. The IoT framework helps you lifecycle management of IoT devices from initial activation, certificate management, rotation and provisioning policies in a more controlled manner. On the bottom right is our business logic, which is the connected vehicle data lake, which is the focus of topic today, where all the telemetry data is stored and processed by enabling various features and applications to customers. So the main focus is this allow organizations across the automakers, across the groups within automakers, where they will drive meaningful insights from the vast amount of data they are collecting from the connected vehicles, leading to improved customer experience, operational efficiency, enhancing operational efficiency, and improved decision making. By exposing the rich set of APIs, enables remote functions that we talked about in the beginning for consumers, and third-party integrations with fleets, EV charging providers, with business intelligent dashboards. And it also enables new use cases leveraging machine learning and generative AI. Next, let's dive into some of the connected vehicle use cases. The use cases are broken down into various categories. Like you see, within predictive maintenance, what is predictive maintenance? It's basically you want to improve your vehicle uptime, reduce maintenance cost, and also improve customer satisfaction, enhance customer satisfaction. The next one is the proactive maintenance, which is really delivering a personalized, data-driven service recommendations that improves overall customer experience, vehicle reliability, and optimized maintenance operations, both for the dealerships. And the third category, which is your vehicle health, this is a critical one where you want to keep updates over-the-air updates to the vehicle to keep the vehicle in check. It also reduces customers' trips to dealerships and overall cost savings for OEMs. And the next one is the vehicle events. Basically, this is where you are tracking the vehicle driving patterns, how the driver is driving the vehicle, especially harsh braking, keeping the oil life in check, speed that helps to do anomaly detection, and timely notification to drivers to improve their driving habits, and also the vehicle lifetime, improve the vehicle lifetime. And of course, event is basically during any event, you want to notify the driver, and the data that is collected helps both during at the time of event as well as during the post-event processing, especially what happened during an incident, and all those data that you collected helps them to come to a closure. Okay, so for all of them, data is crucial for connected vehicles. Like you see in this picture, you have 4 different buckets, which is connectivity is a crucial one for the vehicles to be connected to the cloud, and then accessing data quickly, that is another important aspect. And then you want to maintain the platform cost and make sure it is optimized. And enabled for new use cases, because that is the whole idea of the data is crucial. It goes around continuously in a loop where all these 4 categories are always in check to make sure you enable new use cases and also optimize driver experience. And especially with connected vehicle, data comes with challenges. Like you can think of challenges from a data volume. As more vehicles get connected, the volume grows, and then the complexity. And then there are use cases where you need to have real-time data consumption quickly, close to real time, especially doing remote functions or doing activating some remote features. And then data lake scalability, which is really the critical category where you need to scale for as vehicles increase, connect to the cloud, and how do you handle the high volume and concurrency. And also, you don't want to impact the end users because of the volume. So I think those are the 3 different categories. We see that the data challenge has to be addressed as well. So with that said, I'm going to hand it off to Yanni. She's going to talk about Apache Iceberg on AWS. Over to you, Yanni.
Thank you, Vijay, for that insightful overview of the connected vehicle use cases and the need of a data platform that could handle it. Hey, everyone. Good morning. Happy Monday. Welcome to the first session, Monday morning at re:Invent 2024. I'm Yanni Ambastia. I work on AWS Analytics Services as Analytics Specialist SA. I have over 15 years of experience where I have worked across industry, consulting many companies in building the data strategy and modernizing the data and analytics platform. In my role here at AWS, I work with some of the large automotive and OEM companies where on my day-to-day role, that's what I deal with, the challenges that these customers are dealing with, the data lake side, right? The 3 challenges that Vijay described about. All right, so I'm here excited to share with you as AWS how we are solving these challenges, particularly by modernizing the data lake into using a transactional data lake. Right, so my focus would be primarily that you see here, the bottom right corner, which is the data lake for the connected vehicle, right? And I'm gonna primarily talk about, or briefly just talk about 3 things here before I hand it to a real-world successful story around the same, right? So first one, I'll talk about the evolution of the modern data lake with open table formats. The second one that I would talk about is how Iceberg is evolving and trending. And third one, what does it really bring for the connected vehicle platform, and how does it benefit it? So when we talk about data lake and modern data lake, right, throughout my experience in the industry, I have really seen the evolution happening from a transactional, relational databases to data warehouses to the data lake and then to a transactional data lake, right? And that is where the transactional data lakes with the open table formats is really now the latest trend that we are dealing with, right? So what does it really bring to the table is basically it's blending both the world, where from a traditional data lake aspect, if you think about it, we needed to have a simplicity, maintenance, we need to have ACID transactions enabled, data security. It should enable complex query support. And then on the other side, you have been hearing about this big data analytics and then the open data ecosystem as well, right? So that is what these open table formats is really making it possible to give you a blend of both the world, which is the traditional data lake best practices and then a combination of the open table ecosystem. Prominently, there are 3 open table formats, which probably a few of you or most of you might have already been familiar with, right? So number 1 here that I have, which is Apache Hudi, then Apache Iceberg, and then Delta Lake, right? So these tables are really gaining traction because of the superiority that they're bringing in terms of, they give you a cost-effective, scalable solution for your data lake, right? And that's what making it different from the traditional high format if you have been familiar with, right? And at AWS, we do support all the 3 table formats, and we provide our customers to choose any of the one that suits for their use case. While we support these 3 table formats, lately, you probably have been already familiar as well, the Apache Iceberg is witnessing a widespread adoption. And we have seen over 81% approximately increase in its end users over just a course of 1 year. So think about the scale that it's growing, right? Some of the major companies, you're going to hear the wonderful story from Ford, but additionally, we have Netflix, Airbnb, Adobe. They have already leveraged Apache Iceberg to modernize and build their large-scale big data analytics, right? So this Apache Iceberg comes with a widespread open ecosystem. A lot of cloud providers and vendors are actively supporting and contributing and enhancing the functionality from a transactional data lake aspects, right? For example, at AWS, we are contributing. Then we have our partners, Snowflake, Databricks, Cloudera, and there are many more. I have only the few lists here on the screen, but really there are many more vendors, companies that is contributing to the open source community. And because of that high demand and interest that we are seeing, at AWS, we are positioning Apache Iceberg as strategic open table formats, right? And that's really because of, when we are working with our customer partners on day-to-day basis, we have been continuously evaluating the feedback around how does it perform, how does it interact with the different portion of the data, right? And based on that, really it's making us to kind of think about that our services offering align with the customer needs, our partner needs, and also you can think of the Iceberg as more than the open source community. It's also now being perceived by its ease of use, the performance that it brings to, the scalability that it supports to, right? And that's what it's making for customer a compelling choice to use Iceberg for their data lake and the modernizations. So what is really, it brings the benefit for the connected vehicle. That's what I'm going to quickly summarize here. So first one of that is ACID compliance. So folks who are coming from a transactional database system, probably you might be familiar with, right? How critical for a data operation the ACID compliance is, right? The data needs to be atomic, consistent, durable, and isolated. That is what Iceberg is really bringing to a data lake world, and it's making it transactional data lake world. So how does it matter for connected vehicle? So let me give you an example. So think of that, when a customer, an automotive customer, is having a platform where they're collecting petabyte scale of data from millions of vehicles. And when there is a telemetry data that needs to be inserted into the system or updated into the system, and let's say that there's some system failure happens or some kind of network failure happens, then as a platform owner, you need to ensure that the data lake that you have, it's really in the consistent state, and then it's not having corrupted data just because you had network failure and then partial data got written into, right? Because think of the scale of the risk that it's going to bring to the vehicle safety system when you have some false positive or false negative inputs going to the vehicle safety system. So that is what Iceberg really provides, a reliability and consistency that when the data is getting written into the system, it either completes fully or it doesn't get updated at all, right? The second one here is the schema enforcement and evolution. So what do we mean by schema enforcement here? That means that when you have over the time, the data structure changes. So you need a platform that can handle that schema changes. So for example, in connected vehicle platform, think of like when there is a new telemetry data that needs to be added, right? Or when there is a new feature that needs to be added. So in those scenarios, the data structure could change over the time. And you need to ensure that your platform is able to accommodate those schema changes without disrupting the existing set of data, right? That is what Iceberg is really providing, which is that it gives you the schema evolution. It handles the changes that is happening over the time without for you to need to handle the historical data changes that you have to do. Same goes on to, let's say, the scalability and the performance side as well that Iceberg is really bringing. So when you think about scalability, I talked that customer can have petabyte scale of data. But then on a daily basis, we can get a scale of, let's say, 1 to terabytes of data for a company which is dealing with 1 million vehicles on an average, let's say, right? And if that's generating on an average 10 hours of data. So you need to make sure two things here, right? One, that when you are getting those terabyte scale of data daily, you need to handle the writes efficiently. And at the same time, when you have a petabyte scale of overall data accumulation, you got to have ensured that your end users are able to read it properly, right? That is what Iceberg really provides you. At the same time, it's going to give you scalability to support a petabyte scale of data, and it's going to give you a write scale as well for handling the spikes that you might be getting over the day, right? And then without having the impact on your downstream users. And then the last one here is the engine agnostic, which is really, you can think of that for Iceberg, you can bring your own compute engine, like you can query the Iceberg table from Spark, Trino, Presto, and many other open source. And that's because the open source nature of Iceberg, right? So I won't take much longer time talking about these benefits. Let's just shift the gear from some of these theoretical fundamental concepts that I'm talking about to a real-world story that I would next like to invite our next speaker here, Uma Maheshwara, from our largest customer in automotive, which is Ford Motor, that would be talking through a real-world story that how they revamped their data lake adopting Apache Iceberg. So floor is yours, Uma.
That was a great detail on open table formats and some of the benefits of using Iceberg. Good morning, everyone. I am Uma Maheshwar Gupta Karnati. leading the observability platform development for our Force Connectivity Cloud. I'm super excited here to share some of our learnings or our journey in building the event store, a data lake solution for our observability needs. Yeah, so even before going in details, I would like to quickly give a brief details or overview about our connected vehicle platform. As shown here, what it does, it basically enables the bidirectional communication between the vehicle and the cloud. Being bidirectional, the data can be exchanged on either side, from cars to cloud, cloud to car. This platform right now managing more than 20 million vehicles across the globe. Let me give some real-world example where you can connect to this platform. This platform is really helpful in delivering some of our key functionalities, like ingesting telemetry signals, like maybe reading about your tire pressure, oil levels, fuel level, or odometer reading. And this also play a key role in delivering the software updates over the air to make the vehicle up to date with the latest technologies. The last one, but not the least, it helps in enabling the remote functionality, the one that Vijay was explaining, locking, unlocking, starting and stopping the vehicle remotely. Especially during winter and summer season, we see a heavy volume of the request coming for remote starts. I think, any guesses? The reason in winter we need preheated, and in summer we need cooling, so that we'll have a comfortable experience before getting into the car. So that's a brief overview of our connected vehicle platform. Now, that's it. Then what is Event Store? Event Store is an analytical solution for the platform I just described. So what it does, it basically collects and analyzes, stores various set of events generated from different workflows. It could be the example I explained, the telemetry, or maybe a remote function flow. We call something called commands internally, and a connectivity flow. And this platform is built using Iceberg, powered by AWS serverless technology, mainly Glue and Athena. Both Glue and Athena, being of serverless nature, helped us to eliminate the need of setting up the complex Spark cluster for data processing or a Trino for the querying needs. And it also features a Grafana-based visualization tool so that our users can query the data that's being collected by the platform. And they use this platform for monitoring, for keep tracking some important metrics that's called a KPI metrics, and it acts as a unified platform for querying all the different set of data that I explained, the commands, telemetry, connectivity. It could be any flow. So it's like a single pane of glass to see all the data at one place. Now let's go to the journey. So now I'll go through how we built this solution called Event Store over the time. So when we started, the initial scope was very limited. We were mostly focusing on one particular case called high cardinality data with a moderate data freshness requirement. As everybody looks, the challenge was we want a cost-efficient solution. So with AWS serverless technologies in hand, we were able to quickly develop a solution, and we went live. It was a huge success. Slowly everybody started seeing the immense value of the information from the information it is gathering. So with that, hey, now quite naturally we got requests to, can we onboard other workflows? We onboarded remote functions workflow. Can we onboard telemetry workflow? Can we onboard connectivity workflow? So yeah, slowly in a short span of time, the platform got so many data pipelines onboarded. The data pipeline is basically a pipeline for ingesting a kind of data. So in a short span of time, we are processing much higher volume than expected. So means slowly we started seeing the scalability challenges. Before even going into the details of scalability challenges, I would like to quickly give a high-level architectural flow, how we built when we started. So this is our initial architecture. So it high-levelly has 3 components: the data ingestion component, data processing component, and the last one is acquiring or analytics component. In data ingestion, so we have data producers. These are nothing but the microservices which are making our connectivity cloud platform. They generate events. And we developed a service called Data Lake Service. This basically reads the data generated by the data producers and syncs it to S3. This service is written in Java, implemented using Apache Kafka Connect open source framework. So this service, for every 5 minutes, it flashes the data to S3 from all our producers. That's how the data ingestion layer. Once you got the data into the ingestion layer, nothing but we call a raw zone. And so far, we collected around we have around 2 petabytes of data stored in this ingestion layer or raw zone layer. The second goes to the processing layer. So you have the data now. And we need something to process it and to make it in a more queryable format. That's what the responsibility of data processing layer. So here we have a bunch of glue jobs written in Python, reading the data, applying the required transformation, removing any sensitivity data, doing all the processing logic, and then stores the data into a Hive table format managed by glue data catalog. These tables internally uses S3 as a storage for storing our data, so that we call as a clean zone. That's how we get the data into the clean zone. So that's all about the data processing. So now you have the data. Now that's the last one is about the analytics part. So we use Athena that connected to our glue data catalog where you can query the data that's stored in the system. And Grafana is our visualization tool for general observability needs. So we integrated with Athena using a plugin with that. So users can also use Grafana to query the data that's being stored in our event store. So like I said, we started the project with a very minimal scope, and then after we onboarded many pipelines, and over the time our platform also grown big. With all these things, with all these factors, the data volume is very high. Maybe I'll give an example. For one of the flow, we were getting like 1 million messages per second. So when the platform is receiving that much scale, the data of that much volume, so it started facing the scalability complications. So the implications, there are like I classify it into 4 groups. The first problem we have seen is the glue jobs in the clean zone area are taking more time, the delayed data processing, and slowly our users are seeing a degraded query experience when they're running the queries. Queries used to take longer times, or they may used to fail over the time with some S3 rate limiting exceptions. Many reasons. So the querying is degraded. And over the time, we also saw an increased storage and compute cost to manage this platform overall. And the last one, over the time, the data, we have started seeing the data aging problem. I'll discuss more about the data aging problem at the end. But on a high level, we got these 4 problems to address. OK, so we built the solution. We scaled it. We got the scalability problem. Now let's see how we optimized in our optimization journey. So we went, OK. So we went to the drawing board, like how can we solve it? If you see, the first 3 problems are more into the clean zone area. So let's do, so we came up with a plan of a 2-phased approach. First, fix that clean zone area without changing any architecture. And then that's called the clean zone improvements by doing some optimization to the existing jobs and also adapting the Iceberg. And the last one is further strengthening the platform by adapting the stream processing, by converting our all batch jobs into stream processing using EMR infrastructure. In the optimization journey, the first one is, I just want to recap what we are doing here. So you have jobs written in Python. They read the data, and they write to a clean zone. The main problem we were seeing is more about the pain the platform is experiencing the overhead of listing the files. To explain more, I'm just going in little detail how the job flow works. So let's say we have a data in our raw zone in a directory called flow metrics. We are getting an hour data. Then you have a job scheduled running at an hour 1. It processes the first hour files. Let's say we got 10K files. When it processes, it lists those 10K files, and it writes the data into clean zone. And it also uses something called bookmarking to keep track of what it processed so that it can avoid processing the same data in the next run. Now, after some time, we got, let's say at hour 2, we got 10K more files. Now, in the second run, when the job is running, this time it lists 20K files. And by using bookmarking information, it knows that it has to skip the first 10K files and process only the new data set. So that's how the job processing works with the bookmarking enabled. But just imagine maybe after a week or after a month, let's say at run 100, we got 1 million files because your data is ongoing, right? We keep on getting the data. After some time, we have like a situation where 1 million files are added into our source directory. And when the job trying to process, first it has to list those 1 million files. Naturally, it takes more time to list even before even identifying the new data that it has to process. So we found out that this is the main painful point in the overall job processing time. So how can we, and due to that, sometimes we have seen out-of-memory errors with the Spark driver, which is processing this logic. And how can we fix these out-of-memory errors? Simple. So we have to find out a solution where instead of listing all files, let's list batch by batch. That's something like a lazy loading approach. And that is very simple in Glue. When you use Glue, it's just a configuration called use S3 list implementation true. When you do that, Glue automatically takes care of using a lazy loading instead of loading everything. That helped to solve majority of the problems. And during that process, we also found out some performance bottlenecks with the custom UDFs. Instead, we replaced with the Spark native ones. That gave us some benefits. And as you have seen the logic, so what we identified is instead of keeping the data in the source directory, let's move on to a backup file so that it will reduce the bottleneck of S3 file listing on the Glue job. So with all these things, we were able to address the first problem, that is fixing the delayed data processing times. Now the next problem we were having is the bad query experience. So before even going into the details, let's understand how the query patterns works here. I'm just taking a hypothetical example here. So we have some data in the clean zone that is written by the clean zone data processor. And the table we have, and it is partitioned by year, month, day, hour, and some flow name. So when we can see the data is organized in a directory structure in a S3 folder, like the up to hour level and the flow name levels. So when a user runs a query to find out the count on Athena, what Athena does is it connects to the Glue catalog, identifies the partitions information to locate the files, and it goes to S3, gets those files, does the required calculation, and then gives the results. That is a simple flow. So if you run the query for hour 0 and hour 1, it goes to that S3 folder, hour 0, and hour 1 gets the data. It works really nice when you have a small amount of data. But the examples I was giving where 1 million messages per second flow, the data in those directories we were having like 100K files per hour. So when Athena tries to list those files, identify those, and then read them, naturally we get, in a quick span of time, what we get? We get S3 rate limiting. There is always a limit we can read, right? You cannot read 100K files in a short span of 2 to 3 minutes because Athena is more for a Hadoop querying. So that was the main problem we were facing. The main reason for our query failures we are seeing the S3 rate limiting issues. The main reason is we have so many small files. Small file problem is very common in any data engineering world. So how can we fix? The answer is simple. Can we club them, compact them in a most efficient manner? That way, you save you save the cost as well, because the cost is very huge if you have very small files, and also at the same time you can fix this, the rate limiting issue. So those are the two things we were looking, and also we found out that in our current model, in a Hive table format, changing a column name is always a problem. If you change a column name, you have to reprocess old data. And like that, we have a few other cases we are looking. Then we started, okay, all these problems are related to the format we are using. The scale, for our scale, the I format seems like not working really well to the level what we want. That gave us the direction to finding the Iceberg. So what we did is, we figured out Iceberg is a way for us to go. We didn't change anything. If you see in the architecture initially was using the Hive table format. Now we changed to Iceberg format. So migration was simple. So what we did is, first, initially our users were using the tables directly. Instead of direct table access, we created a view with an existing table, and we asked our consumers to use the views instead of tables. It's like a reference to the root table. Now, we created a table in the Iceberg format, and then updated our jobs to write the new data to the new tables, and also updated the view to point both the legacy table and also the new table, which is in Iceberg format. This way, we were able to migrate without any downtime. And Iceberg also provides the table compaction. By using this table compaction, we were automatically able to compact all those small files into a decent size. That can be done by calling a bunch of Iceberg functions. We were running a special jobs initially to do that, but recently AWS implemented this as a serverless feature. You can just go to Glue and apply some configuration that will take care of doing the table compaction without managing our own custom job for running the Iceberg table compaction. So that was also a good add-on for us. With all these things, we were able to get these results. So if you see the first slide, it's about the query in Hive format. And when the query took around 1 minute, 39 seconds, for the same table after the Iceberg migration, we have seen around 12 seconds. That's almost an 80% improvement. So it was taking 80% less time compared to the other. If we do a deeper look at the view, in the Hive table, the problem was more on the planning side because it was struggling to locate the files. Whereas in Iceberg, it's easy because Iceberg uses its own metadata layer to quickly find out the related files based on your partition columns. So that was the big differentiator for fixing all our querying experience and also saving the S3 cost. So with all these things, this is what we reached. So our architecture remains same, only the major changes adapting to the Iceberg. So with this solution, we were able to fix the first 3 problems, fixing the job processing times, fixing the query problem, and by using 1 and 2, we also saved the cost because S3 cost is much lesser compared to what we had earlier. And in these 3 layers, like each stage, we take like 5 minutes time. So we take a minimum 10 minutes plus the processing time to process any data and store in event store. This is our journey so far. Now, what we can do better? That's what we are looking. So the next stage is, can we make this platform further better by adapting the stream processing framework? So how can we? One of our customers are our production engineering team. They heavily depends on this data, especially when troubleshooting any incident to identifying the impact analysis. Maybe they want to know how many vehicles got impacted for a particular outage. And they just they just use Grafana and query our database, and they get the data. But the problem for them is they cannot wait even for 10 minutes because the situation is like that. How can we build? So we have a different set of users. For these users, we figured out doing batching may not be a good solution. Instead, provide a solution where you can support both streaming and batching. Streaming is for more real-time use cases. So what we are doing is this ongoing work we are doing. So in the clean zone, we'll be running our Spark jobs, running on EMS serverless, reading the data from the data producers, and directly writing to Iceberg, so that there is no delay. We are directly reading the data from the topics generated by the data generated by the producers and writing to Iceberg. So the data is almost available as early as possible. And we're also running other jobs, so for backup purpose, so that we can use using the same streaming approach, but we are writing the data as a raw data into a backup S3, direct S3, so that we can use this data for any future processing or future feature development. So this way, we were able to address all our issues, and we set out what we can do better using the streaming. So with these details, I would like to hand over to Yanni to give the conclusion on what we can do better with Apache Iceberg.
Thank you, Uma, for such a compelling and impactful, successful story that you just briefed us about. So, the real-world experience that Uma just shared, it's telling us that, the impact that it's bringing by adopting to Apache Iceberg, it's not simple and open table format that you can think of, but it's really driving how you can modernize your transactional data lake, right? And that too for batch workloads, for streaming workloads, and for the data when you have to deal at scale. So as we conclude here, I just want to emphasize the transformative power of using Apache Iceberg with AWS analytics services here. So on the left, you will see some of the trending use cases and the features that Iceberg provides, right? And some of them, like the small file problems and how compaction really solves that. You heard that from Uma's event store story, right? There's more to that, actually. It can handle the processing and the storage management even for semi-structured data as well, on top of structured data. Then you have multi-engine support that I talked about, right? So those are really the Iceberg innovative features that is helping us. But then what is really truly distinguishing it is that a comprehensive support of Apache Iceberg table that we have from our AWS ecosystem of the services, which you are seeing on the right here, okay? So we have Amazon EMR that our customers use for big data processing for the analytics workload. Then we have AWS Glue, that is for building ETL workflows. Amazon Athena, you heard that from Ford's story as well, right? These services that is used for serverless querying. Then on the ML side as well, we have been seeing really the evolution that customers are trying to do by querying the Iceberg directly from the machine learning services like SageMaker that we have. For analytics and warehousing workload, we have Amazon Redshift. And the good part is that all these services seamlessly support Apache Iceberg, right? And with the simplicity of SQL languages that you can just query these tables, which is being sitting into the transactional data lake. Recently, we have added the Amazon Data Firehouse to this family as well, just to streamline the real-time streaming workload that could go into the transactional data lake based where you're going to storing into Iceberg, right? And then in the center of all this integration, we have AWS Glue Catalog. That is giving us a unified metadata repository that's going to make all these services interoperate with each other while you having a unified catalog that is supported by Glue Catalog. And then when it comes to Iceberg, there are a lot of optimizations, like compactions that Uma described about. You got to handle that over the time. And that is what we are trying to enable, part of the Glue catalog, that we add on these optimization options for our customers. And then, underpinning all of this, you have Amazon S3, where you're going to be storing Iceberg for your transactional data lake, and that's going to provide you a cost-effective, scalable solution for your transactional data lake, right? So that's kind of pretty much it, was our session. As we draw our session to a close here, I really like to thank all of you to choosing to spend your Monday morning with us.